A raw, pre-trained base model has no inherent concept of being a helpful assistant. It's a statistical engine designed to predict the next likely token. While pre-training injects vast world knowledge into the model's weights, that knowledge is unorganized. The model lacks the specific logic required for safe, structured conversation. The process begins with supervised fine-tuning, or SFT, establishing basic conversational structure. Next is rejection fine-tuning, or RFT, providing a framework for autonomous logic. Finally, direct preference optimization, or DPO, aligns the model's outputs with subjective human taste and safety constraints. Chaining these three mathematical loss functions creates a systematic approach to addressing the raw model's limitations. Supervised fine-tuning relies on teacher forcing. We provide the model with thousands of expert-crafted examples of perfect prompt and response pairs. The goal is behavioral cloning. We are forcing the model to adopt the distinct cadence and formatting of an assistant. This is achieved through loss masking. We apply a zero multiplier to the prompt tokens, so the model only learns from the completion. In this cross-entropy loss equation, gradients are only updated based on the assistant's response. If the model predicts an incorrect token in this highlighted response area, the penalty curve spikes. The limitation of SFT is that it encourages the model to memorize static, expert-provided paths, rather than understanding the underlying logic. This leads to distribution sharpening. The model's output probability collapses into a narrow set of expected templates. When the distribution is too sharp, the model loses the variance needed to explore alternative solutions or perform trial and error reasoning. SFT builds a successful conversational interface, but its reliance on imitation limits the model's ability to solve novel logical problems. To restore the model's ability to solve verifiable tasks like math and coding, we employ rejection fine-tuning. Instead of providing a static answer, the system forces the model to generate multiple independent reasoning trajectories, or rollouts. An automated verifier, like a Python compiler, then scores these trajectories objectively. Only the successful paths are retained. Standard RFT discards the failed attempts and uses only the successful trajectories to update the SFT loss function. Discarding these failures is inefficient, as failed trajectories often contain valid intermediate reasoning steps. Step rejection fine-tuning, or SRFT, was developed to address this data waste. SRFT rescues those paths by applying the zero-loss mask only to the specific token that caused the logical error, preserving the correct steps that preceded it. Reward-informed fine-tuning, or RIFT, takes a different approach by multiplying the log likelihood by a scalar reward value. This allows the gradient updates to scale based on the quality of the trajectory. RFT transforms the model into a reasoning engine capable of generating internal logic steps to navigate complex problems. Logic and math are verifiable, but they don't cover subjective human preferences like tone, politeness, or safety guidelines. Traditional reinforcement learning from human feedback addressed this alignment, but required 4 models to run simultaneously, creating a massive hardware bottleneck. Direct preference optimization is a mathematical breakthrough that achieves alignment using only 2 models. DPO uses a pairwise preference dataset. For every prompt, the model is shown one chosen response and one rejected response. Using the Bradley-Terry model, DPO calculates the probability gap between the 2 responses. The complex partition function cancels out, leaving the difference in logics. The model directly optimizes the policy to increase the probability margin between the desired behavior and the rejected one. To prevent the model from drifting too far from its original logic, a frozen reference model acts as an anchor. The KL divergence penalty ensures the model remains grounded in its previous training. By utilizing relative probabilities, DPO sculpts the model's final persona, ensuring its output aligns with human taste and safety requirements. SFT, RFT, and DPO function as sequential stages within a unified post-training pipeline. Phase 1 establishes the formatting, Phase 2 expands the reasoning boundaries, and Phase 3 performs final alignment. Operating this pipeline on a GPU cluster introduces extreme VRAM constraints. Loading the policy and reference models side by side often pushes hardware to its absolute limit. This memory pressure makes the choice of DPO, which only requires 2 models, a necessary hardware decision for many engineering teams. One of the most frequent causes of pipeline failure in production is a formatting mismatch between the SFT training phase and the DPO inference phase. If chat templates and data schemas are not perfectly consistent across all three stages, the loss functions will calculate gradients on the wrong tokens and degrade the model. This engineering journey transforms a passive statistical parrot into a cloned assistant, an exploring reasoner, and finally, a safely aligned AI agent. Command of these three loss functions is the requirement for architecting frontier AI systems.